Imagine a problem so vast, so complex, it'd tie up even our best classical supercomputers for, like, thousands of years. Now, what if a completely different kind of machine, working on totally different principles, could crack that same problem in minutes, or maybe just hours? That's the truly mind-boggling promise of quantum computing.
And that's what we're diving into today. It's our mission, really, to distill the essence of that promise. We're stepping into a field that, yeah, often sounds like pure science fiction, but it's deeply rooted in the fundamental laws of the universe. We've got a stack of sources here, a big Wikipedia overview, insights straight from IBM, and we're going to sift through it all. Uncover the core concepts, the surprising history, and the very real challenges, and yes, the huge potential. We want to give you a clear, comprehensive understanding of what quantum computing actually is, and crucially, why it matters to you.
Right, because we're not just talking about a faster version of your laptop, are we? This isn't just Moore's law continuing.
Not at all. Quantum computing fundamentally rethinks how computation even works. It harnesses the bizarre counterintuitive rules of the quantum world, the very, very small.
Okay, so where do we start? What's the basic building block?
The qubit, the quantum bit, that's the heart of it. See, a classical bit, it's simple. It's a 0 or a 1, that's it. But a qubit, it has this incredible ability to exist in a superposition of both 0 and 1 simultaneously.
Both at once. How does that even work?
It's like, think of it as a weighted combination. It's not just on or off, it's leaning towards both states at the same time. And this seemingly small difference, it unlocks exponentially more powerful computational spaces. For you, this means a completely new way of tackling complex problems that are just impossible for classical machines today.
Okay, it's definitely a strange world we're entering. So to really get a handle on what's going on inside these machines, you said there are key principles.
That's right. 4 main ones to understand the basics: superposition, entanglement, interference, and the big challenge, decoherence.
Let's start with superposition then. You said it's being 0 and 1 at the same time?
Exactly. A qubit's ability to be in multiple states simultaneously. Like a spinning coin before it lands, it's kind of heads and tails. This creates those vast, multi-dimensional computational spaces. It lets us represent complex problems in totally new ways. But, and this is key, when you measure it like slapping that coin down, its state collapses.
Collapses?
Yeah, it falls out of that superposition of possibilities into just one single definite classical state, either a 0 or a 1.
So if it collapses when you look at it,
Yeah.
how do you compute with it? Doesn't that ruin the quantumness?
That's the clever part. You perform quantum operations, these quantum logic gates, before you measure. You manipulate the superpositions while they exist, but to really unlock the power, especially with multiple qubits, you need the next principle, something even weirder.
Which is?
Entanglement.
Entanglement. Einstein's spooky action at a distance. This is the one where qubits get linked, right?
Intrinsically linked, yeah. It's fascinating. When qubits are entangled, they become perfectly correlated. Measuring one instantly tells you something about the state of the other, no matter how far apart they are. It's like they share a single destiny.
Wow, okay. And that linkage is useful for computing.
Absolutely critical. It's a key resource. It lets qubits work together in complex ways that classical bits just can't. It forms the backbone for their unique processing power.
Okay, so we have qubits being in multiple states, superposition, and linked fates, entanglement. What's interference? You said that's the engine.
It really is the engine. Interference is how quantum computers actually find the answers. Think about waves. Qubits in superposition behave like waves. When wave peaks meet, they amplify that's constructive interference. When a peak meets a trough, they cancel out destructive interference.
Like noise-canceling headphones.
Kind of, yeah. A quantum computer uses carefully controlled interference patterns. The algorithm is designed so that the waves corresponding to the wrong answers cancel each other out. Destructive interference. And the waves for the correct answer reinforce each other. Constructive interference. They get amplified.
So the interference sort of filters out the noise and boosts the signal being the right answer.
Exactly. It sifts through this huge space of possibilities opened up by superposition and entanglement and zeroes in on the solution by amplifying it.
Okay, let me see if I've got this. You start with qubits in superposition.
Prepared in a specific initial state.
Then you use quantum gates to entangle them and set up these interference patterns based on your algorithm.
Right. The circuit guides the evolution of the quantum state.
And the interference cancels out the wrong paths and boosts the right one, which you then measure at the end.
You've got it. That's the essence of how a quantum computation works. It's this incredibly delicate dance.
Delicate sounds right. Which brings us to the spoiler, right?
Yeah.
Decoherence.
Ah, yes. Decoherence. The arch nemesis of quantum computing. It's basically the loss of that precious quantum state. The quantumness just dissipates.
What causes it?
Interaction with the environment, anything really. Stray heat, vibrations, electromagnetic fields, even a single cosmic ray hitting a qubit. Or just the act of measuring it, as we said. Think of a perfectly tuned guitar string. The slightest touch, a puff of air, and the pure note is gone.
So keeping these qubits quantum is hard.
Incredibly hard. It's one of the biggest engineering challenges. You need extreme isolation, ultra-high vacuum, and extreme cold. We're talking temperatures near absolute zero, often around 20 millikelvin, just fractions of a degree above the coldest possible temperature.
Wow. And even then, they still decohere.
Oh, yeah. It happens fast. Milliseconds, sometimes even faster. This limits how long a quantum computation can run. Your whole algorithm has to finish before the system decoheres. Everything needs to be incredibly fast.
Okay, so the physics is wild. But this isn't a brand new idea, is it? When did people start thinking about computing with quantum mechanics?
No, not brand new at all. The seeds were planted back in the 1980s. You had Paul Benioff in 1980 describing a theoretical quantum Turing machine. And then, independently, Richard Feynman and Yuri Manin, both brilliant physicists, suggested around the same time, hey, maybe we could use quantum phenomena themselves to simulate quantum systems.
Because simulating quantum mechanics on a classical computer is super hard.
Exponentially hard, yeah. So the idea was, let quantum systems simulate themselves. That was a really key insight.
So that was the theory. What about the moments where it started to look like it could actually do something practical, the breakthroughs?
Well, things started moving. In 1984, Bennett and Broussard came up with quantum cryptography, QKD quantum key distribution.
That's about secure communication, right?
Exactly. Using quantum principles to create fundamentally unbreakable encryption keys. That was a really different kind of application. Then came this idea of quantum parallelism. Early algorithms like Deutsch's, Bernstein-Vazirani, Simon's algorithm, they showed something amazing.
What was that?
They showed that by putting a qubit into superposition, you could essentially evaluate a function for multiple inputs at the same time. One query could give you more information than classically possible. It hinted at speedups.
Hints. But then came the big one.
Then came the earthquake. 1994, Peter Shor, his algorithm for factoring large numbers.
Ah, the encryption breaker.
That's the one. Shor showed a quantum computer could factor numbers exponentially faster than any known classical algorithm. And since most of our modern public key encryption, like RSA and Diffie-Hellman, relies on factoring being hard, well,
suddenly everyone paying attention.
Yeah.
Governments, security agencies.
Instantly. It put quantum computing firmly on the map as something with potentially world-changing implications. And then just 2 years later, in 1996, Love Grover came up with his search algorithm.
What did that do?
It offered a quadratic speedup for searching unstructured databases. Not exponential like Shor's, but still significant for many problems. It showed quantum wasn't just a one-trick pony for factoring.
Okay, Shor's algorithm, Grover's algorithm, these showed potential. Which leads to this term we hear a lot, quantum supremacy. It sounds like game over, classical computers lose. What does this really mean?
Yeah, the term itself is a bit loaded, maybe controversial. John Preskill coined it. Quantum supremacy isn't about solving a useful problem faster. It's more of an engineering milestone. It's demonstrating that a programmable quantum device can perform any calculation, even a contrived, useless one, that is provably beyond the capabilities of even the most powerful classical supercomputers we have today.
Like a proof of concept, but at scale.
Exactly. Google, working with NASA, made a big splash claiming this in 2019 with their Sycamore processor. They ran a specific random circuit sampling task they said would take Summit, then the world's fastest supercomputer, 10,000 years.
IBM pushed back on that, didn't they?
They did. IBM argued that with better classical algorithms and using Summit's full capabilities, the task could be done in maybe 2.5 days. Still long, but not 10,000 years. Then, China's USTC group demonstrated supremacy with their Jizang photonic computer in 2020 using a different task, boson sampling. And while a 2024 study did manage to directly verify some of these claims using a next-gen supercomputer, the whole debate really highlights the difference between a scientific demonstration, a look what we can do, and actual practical application.
So it's like climbing Mount Everest. Impressive feat doesn't mean you can use it for your daily commute.
That's a pretty good analogy, yeah. It shows the hardware is reaching a certain level of power and control, but it doesn't automatically translate to solving real-world problems better yet.
Okay, so if it's not just a faster desktop and supremacy is more of a benchmark, what are the real-world problems these machines are expected to be good for? Where might we see the first actual advantages?
Broadly speaking, there are two main areas where experts expect quantum computers to really shine. First, and perhaps most naturally, is modeling physical systems.
Like Feynman's original idea.
Exactly. Quantum mechanics basically governs chemistry, material science, particle physics. It's the operating system of the universe at that scale. Simulating these systems accurately is often impossible for classical computers because the complexity grows exponentially. But a quantum computer is a quantum system. It can potentially simulate other quantum systems directly.
What kind of simulations?
Think drug discovery. Designing new molecules with specific properties by accurately predicting their quantum behavior. Not just searching existing libraries faster, but designing novel drugs from scratch. Materials science, designing new catalysts, maybe for more efficient fertilizer production. Ammonia synthesis currently uses like 2% of the world's energy. Finding a better catalyst could be huge. Or understanding high-temperature superconductors, developing new battery technologies, even probing fundamental physics in particle colliders, or understanding protein folding better.
It's like instead of crunching numbers about the molecule, the quantum computer becomes the molecule, in a way.
That's a great way to put it. It mimics the system directly.
Okay, that's modeling physical systems. What's the second area?
The second broad area is identifying patterns and structures in information. Quantum algorithms, because of superposition and entanglement, can process data in fundamentally different ways. This could lead to breakthroughs in fields like finance, maybe optimizing complex portfolios or certain types of machine learning problems. For instance, using quantum approaches for generative models, perhaps even applied back to drug discovery in a different way.
Interesting. So, modeling the physical world and finding hidden patterns in data. Let's circle back to security, though. Shor's algorithm. Is our digital world about to crumble?
It's definitely a serious concern. The potential impact is huge. Shor's algorithm, if run on a large enough fault-tolerant quantum computer, could break the public key encryption like RSA and Diffie-Hellman that protects most secure communication online today. Your bank, your emails, secure websites.
And Grover's algorithm.
Grover's offers a quadratic speedup for search, which means it could effectively have the strength of symmetric encryption keys like AES. It makes brute force attacks more feasible, meaning we'd need longer keys. So yes, there's a significant threat. The race is on to develop and deploy quantum-resistant cryptography before such computers exist.
But you mentioned quantum offers security opportunities, too.
Absolutely. That's the other side of the coin. Quantum mechanics itself offers ways to create secure communication. Quantum key distribution, QKD, uses the principles of quantum measurement, the fact that measuring disturbs the system to allow two parties to generate a secret key, knowing that any eavesdropper would inevitably leave detectable traces. There are also quantum random number generators, QRNGs, which can produce truly unpredictable random numbers, vital for strong cryptography.
So quantum breaks and quantum fixes.
In a sense, yes. And the world is actively working on the fix. There's a whole field called post-quantum cryptography, PQC. NIST, the U.S. standards body, is in the final stages of standardizing new classical algorithms that are believed to be resistant to attacks from both classical and quantum computers. The goal is to transition our infrastructure to these new standards.
Okay, that's somewhat reassuring. Now, you mentioned the economic potential, a USD 1.3 trillion industry by 2035. That sounds massive. Is that realistic given all the challenges?
The projections are huge, and they reflect the potentially transformative nature of the technology. It's not just about doing current things faster. It's about enabling entirely new industries and solutions. Think about the impact of discovering a room-temperature superconductor or revolutionizing drug design. The economic value could be immense, and you see the investment pouring in major tech companies like IBM, Google, Microsoft, Amazon, Intel, plus numerous startups and significant government funding globally. But yes, realizing that potential means overcoming those monumental engineering hurdles we talked about.
Right, let's dig into those hurdles. We mentioned DiVincenzo's criteria. Scalability, initialization, gates, faster than decoherence, Universal gates, readout.
Exactly. Those are the fundamental requirements. You need to be able to build systems with many high-quality qubits, scalability. You need to set them to a known starting state reliably, initialization. Your quantum operations, the gates, need to be quick and precise, finishing before decoherence wipes out the quantum state. You need a set of gates that can perform any possible quantum computation, universality. And you need to measure the final state accurately, readout.
And controlling all those qubits at once must be tricky too.
Hugely tricky. Generating and coordinating maybe millions of precisely timed electrical signals to control the qubits without introducing noise, that's another massive scaling challenge for the control systems.
But the absolute biggest headache is still decoherence.
Without a doubt, it's the fundamental enemy. Maintaining that fragile quantum coherence long enough to do something useful. We talked about the extreme cold, the isolation, but even then, tiny fluctuations, stray particles like cosmic rays, can knock a qubit out of its state. And this fragility forces us towards quantum error correction.
Error correction, like in classical computers.
Similar in principle, but much, much harder in quantum, because you can't just copy a quantum state to check it. Measuring destroys it. Quantum error correction involves encoding the information of one logical qubit across many physical qubits. These physical qubits work together to detect and correct errors without actually measuring the underlying logical state.
But that sounds like it needs a lot more qubits.
A lot more. That's the overhead. Remember that example? Factoring a 2048-bit number might take, say, a few thousand logical qubits, but implementing the error correction could require millions of physical qubits.
Millions. Wow, so we're still a long way from having millions of stable physical qubits.
We are. Current systems are in the range of hundreds, maybe low thousands of physical qubits. Getting to millions with high enough quality and connectivity is a huge leap.
Are there different ways people are trying to build these physical qubits? You mentioned a few approaches.
Yeah, there's no single winning technology yet. Several promising candidates. Superconducting circuits are popular, used by Google and IBM. They're fast, relatively easy to fabricate using standard chip-making techniques, but they need those extreme millikelvin temperatures. Trapped ions, individual atoms held by electromagnetic fields, are another leading approach. They have amazing coherence times, meaning they stay quantum for longer, and very high gate fidelities, but they tend to be slower than superconducting qubits. Then you have quantum dots, tiny semiconductor crystals, photonic qubits using single particles of light, great for communication but challenging for computation. And there's a more exotic approach called topological quantum computing. Microsoft has been investing heavily in this. It uses quasi-particles called anyons whose properties are supposedly inherently protected from local disturbances, potentially making them much more fault-tolerant. But it's still very much in the research phase.
So lots of different paths being explored, given all this.
Yeah.
The fragility, the error correction overhead, the different qubit types. Where are we really? Are these things actually useful yet for anything beyond research?
That's the million-dollar question, isn't it? And you have to be realistic. That Nature article from 2023 basically said, for real-world problems right now, current quantum computers are good for absolutely nothing.
Ouch.
Yeah. But it also stressed their likely long-term utility. The point is, while they might solve some specific mathematical problems faster in contrived demonstrations, they don't yet offer a practical advantage for general tasks compared to our best classical methods. And classical computing isn't standing still. Algorithms get better, hardware gets faster. Sometimes a clever new classical algorithm emerges that can match or beat a proposed quantum advantage. Some quantum algorithms have even been dequantized.
Dequantized, meaning they found a fast classical way to do it.
Exactly. It shows the boundary is constantly shifting. It's not a fixed target.
So if supremacy is debatable and practical use is nothing right now, how do we measure progress? What are the new goalposts?
The field is moving towards more nuanced milestones. Two key concepts now are quantum utility and quantum advantage. Quantum utility is about showing that a quantum computer can provide reliable solutions to scientifically or industrially relevant problems that go beyond what's possible with brute force classical simulation, even if approximations were used before. IBM demonstrated this first in 2023, modeling aspects of a magnet.
So useful science, even if not strictly better than all classical methods.
Kind of. It's solving problems classical methods struggled with accurately. It shows the quantum approach works for real science. Quantum advantage is the higher bar. That means demonstrating a quantum computer can provide a solution that is significantly better, faster, cheaper, or more accurate than any known classical method for a specific practical problem. IBM is aiming to demonstrate the first instances of quantum advantage by late 2026, but they stress it will likely require close integration between quantum and classical high-performance computing.
Okay, utility first, then advantage. How are companies like IBM tracking their progress toward those goals? Are there specific metrics?
Yes, they're developing better benchmarks beyond just qubit count. IBM talks about things like layer fidelity, basically how well the processor runs quantum circuits layer by layer. It gives a sense of the overall quality and error rates. CLOPS, circuit layer operations per second. This is meant to be a measure of speed, capturing how many layers of a typical circuit can be run reliably in a second. It includes both quantum gate speeds and classical processing overhead. And circuit depth. How many layers of gates can you run before decoherence kills the computation? Deeper circuits mean you can tackle more complex problems.
So better quality, faster execution, and longer computation times. Makes sense. What does IBM's roadmap look like for scaling this up?
They have ambitious goals. They're targeting a system with 200 logical, error-corrected qubits by 2029. That system should be capable of running circuits with 100 million gates.
200 logical qubits. That would require many more physical qubits, right?
Potentially tens or hundreds of thousands, depending on the error correction efficiency, which is why breakthroughs in error correction are so vital. IBM announced a new code in 2024 they claim is 10 times more efficient, which could significantly reduce that overhead. Looking further out, they aim for 2,000 logical qubits running 1 billion gates by 2033.
1 billion gates.
Yeah. The vision is clearly heading towards what they call quantum-centric supercomputing. It's not quantum replacing classical, it's quantum processors tightly integrated with classical CPUs and GPUs working together, each tackling the parts of a problem they're best suited for.
A hybrid future. Okay, this brings up a really fundamental question. We talked about speed. But can quantum computers solve problems that are theoretically impossible for classical computers? Do they change what's fundamentally computable?
That's a deep question, touching on the theory of computation. And the answer, in terms of computability, is generally believed to be no. Any problem that can be solved by a classical computer, a Turing machine, can, in principle, be solved by a quantum computer, and vice versa. Quantum computers don't seem to violate the Church-Turing thesis, which defines the limits of what algorithms can compute. They don't let us solve fundamentally unsolvable problems like the halting problem.
Okay, so they don't change the what, but they change the how fast.
Exactly, that's the key difference. It lies in computational complexity, how the resources, like time or memory, needed to solve a problem scale with the problem size. Quantum computers are strongly suspected, though not rigorously proven for all cases, to solve certain problems much faster than classical computers. Exponentially faster in some famous cases. Computer scientists talk about complexity classes. Problems solvable efficiently by classical computers are in the class P. Problems solvable efficiently by a quantum computer are in the class BQP, bounded error, quantum polynomial time.
And BQP is bigger than P.
It's believed that BQP contains problems that are not NP integer factorization. The problem Shor's algorithm solves is known to be in BQP, but it's widely believed not to be in P. That's the source of the potential quantum speedup. So they operate within the same ultimate boundaries of computability, but they seem to navigate the landscape of computational complexity much more efficiently for certain types of problems.
Wow, what a journey through the quantum realm. Seriously, mind-bending stuff. From superposition and entanglement, those bizarre building blocks, through the history of the algorithms like Shor's, the huge engineering challenges like decoherence and error correction, and now this vision of quantum-centric supercomputing aiming for utility and advantage, potentially driving a trillion-dollar industry. Really, it feels like we're on the cusp of redefining what's computationally possible.
It absolutely does. And it's clear, we're not there yet. You won't have a quantum computer on your desk next year. But the foundational science is solid, and the engineering is progressing at an incredible pace. Breakthroughs are happening constantly, and the future, as we discussed, likely isn't quantum versus classical. It's a powerful synergy. These machines working together, tackling problems in science, medicine, materials, AI problems that have just been completely out of reach for us until now.
So for you listening, as you think about the future of technology, here's maybe a final thought to chew on. As these quantum machines get closer to achieving real utility, real advantage, what's that one currently impossible problem in your world, your job, your field, maybe even just something you wonder about that a quantum computer might be the first to crack? What previously unthinkable question might they finally answer?